Scientists call this the greenhouse effect.
It would curb acid rain by reducing...
Avoid contamination on the beaches.
Meanwhile, the combination of heat and pollution...
Global warming brings along the possibility.
Envios de desperdicios tóxicos.
Dire consequences.
Yakety yak, yakety yak.
What are they talking about? Let's find out.
Hi, I'm Dr. Miller Hughes Fulford. Welcome to the Chevron Video Showcase Series, EcoSpeak, Coming to an Understanding. What you see here is the interior of NASA's Space Shuttle Columbia, where I made my first space flight in June of 1991 as a medical investigator and scientist astronaut. When you're off planet and you look at the Earth, it glows and shimmers like it's alive. And behind it, there's nothing but black void. You see that the Earth is all alone in space, and you realize that it must be protected and preserved. And we, you and I, are the people who will have to do that. We hear a lot of catchy phrases about our environment, and a lot of scary predictions about the Earth's future, but it's not always easy to understand what people are talking about or to know what to believe. Most environmental issues are very complicated, and there are no quick fix solutions. Even scientists themselves disagree about many of the issues. We call this series EcoSpeak, Coming to an Understanding, because each program is about a word or a phrase concerning the environment that we've all heard but may not understand very well. We've asked some of our country's leading environmental scientists and other experts to help us understand these issues based on scientific knowledge. This program is about what some people call the hole in the ozone. It's also known as ozone depletion and ozone thinning. The word ozone comes from an ancient Greek word meaning odor, and ozone is a pale blue gas with a strong odor. Near the Earth's surface, ozone is part of air pollution, but high above the Earth, it protects life as we know it. In this program, we talk about that high ozone, what people call good ozone. We talk about ground level or bad ozone in the program on smog. Watch for this. When you see it, we'll challenge you with a question that we want you to think about, and we'll answer it at the end of the program.
Thank you.
Now, let's look again at the Earth from space, because to understand what the hole in the ozone means, we have to start with the atmosphere, that thin blue shimmer you see around the Earth. Scientists describe the four major layers of the atmosphere according to density and temperature. There are no really sharp divisions between them. Each part of the atmosphere blends up into the next. For this program, let's focus on the two lower layers of the atmosphere.
Here's where we live, in the lower part of the atmosphere. We call this the troposphere. It goes up about 7 to 8 miles above the Earth's surface, and it's where nearly all our weather happens. This is the air we breathe. Today, airplanes, satellites, and the space shuttle let us look at the Earth's atmosphere in new ways. We can track weather fronts, we can watch the movement of a hurricane, and we can see just how far dust storms and volcanic ash and smoke from huge fires can travel. You see it every night on TV. It gets pretty cold high up in the troposphere. In fact, it gets real cold. It's about 75 degrees below zero here, colder than the inside of your freezer. Up higher, the air gets even thinner. This is the stratosphere, and it stretches up from about 8 to 30 miles.
And it's here in the second layer of the atmosphere that our story of the good ozone begins. About 12 to 20 miles up, the ozone layer that we've all heard so much about is formed. Let's watch how this happens as we follow the sun's energy racing toward the Earth.
So sunlight streams out from the sun and heads towards the Earth with the speed of light, which is 186,000 miles per second, so it gets here in about 9 minutes. This is solar energy. It makes up what scientists call the electromagnetic spectrum. The sun radiates different wavelengths of this electromagnetic spectrum, called gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, and radio waves. About half the energy in this radiation is visible, and it looks white to our eyes. But when we look at it through a prism like this, we see all the colors of the rainbow.
Solar energy heats the surface of the Earth, which then gives off the infrared heat that is radiated back to space. So UV radiation helps heat the Earth, but too much is not good for us. Now, let's say that we're floating in space and we're not protected in any way. Solar radiation is traveling so fast and is so full of energy that if it would hit us directly, it would attack the DNA in our bodies and destroy our cells. But here on Earth, we're safe. We're protected from the really dangerous parts of solar radiation. And what protects us? The atmosphere. It's what makes life on Earth possible. Now, let's look at how the ozone layer is created when sunlight strikes our atmosphere.
The most powerful colors of sunlight, gamma rays and X-rays, are absorbed high in our atmosphere, but the other colors of sunlight continue on down toward the ground. Then in the middle of the stratosphere, some of the oxygen molecules are hit by sunlight. The ultraviolet radiation smashes into these molecules, and the energy from the collision splits them into two single oxygen atoms. But a single oxygen atom is very unstable. It wants to hook up with something in the worst way, so it bounces around until it finds something that it can bond to, like an oxygen molecule. So now 3 oxygen atoms are bound together, and this is ozone. Ozone doesn't continue to build up forever in the stratosphere. The ozone molecules are struck by incoming ultraviolet rays. They break apart into new oxygen molecules and single oxygen atoms. Ozone is constantly being produced, destroyed, and then produced again, forming what we call the ozone layer. It takes a lot of energy for all this to happen, so most of the sun's ultraviolet radiation is absorbed in the process.
Ozone is actually quite rare. There are only 10 ozone molecules for every million molecules of other gases, and the ozone layer is not spread evenly around the Earth. Most ozone is created near the equator, where there's more sunlight, but it's rapidly blown north and south by the prevailing winds. There's actually 50% less ozone above the tropics than at higher latitudes. That's one reason it's easier to get a sunburn in Florida or Hawaii or Africa than it is farther north. There's less ozone in those areas, so more UV rays get through to the Earth itself. Another reason for more tropical sunburns is that the sun shines more directly on the Earth in those areas. The formation of the ozone layer is a natural process that absorbs nearly all of the most dangerous kinds of solar radiation before they reach the Earth. This creates kind of a natural balance that protects and sustains life. So what do people mean when they talk about the hole in the ozone? We'll look at that next.
What happens when you spray your hair, turn on the air conditioner in a car, open a refrigerator door? Are you releasing CFCs into the air?
Thank you.
Today we hear people talking all the time about the hole in the ozone. But what do they mean? Well, as you heard earlier, everybody seems to mean something different. There's been a lot of controversy and confusion about the Earth's ozone layer. Scientific investigators have to be detectives when they try to discover what's really going on. First of all, the hole in the ozone is not actually a hole, not technically anyway. Scientists call it ozone depletion or ozone thinning. It means that there are now fewer ozone molecules in some parts of the stratosphere than there were 10 to 15 years ago. And what causes ozone depletion? Well, today, scientific evidence indicates that even though the depletion happens high up in the stratosphere, it's caused mostly by human activities down below. The idea that human activities might impact the ozone layer is not really new. As early as the 1970s, scientists predicted that exhaust emissions from fleets of supersonic transport aircraft flying through the stratosphere might cause ozone depletion, which could ultimately affect human health. Only a small number of these planes were ever built, though, so the predictions were never tested. Then some scientific discoveries were made that led to what's been called the ozone wars. To get to the beginning of this controversy, we've got to go back even further in time. In the 1930s, some chemical compounds called chlorofluorocarbons were developed. You've probably heard them referred to as CFCs. CFCs contain chlorine, fluorine, and carbon, and are very useful in refrigerators, air conditioners, spray cans, solvents, foams, and other products. In those early years, CFCs didn't seem to have any bad qualities at all. They were considered to be the perfect chemical compounds because they were non-toxic, non-flammable, non-corrosive, and non-reactive. Many years went by before scientists began to realize that the very qualities that made these compounds safe also let them exist for years to pile up in the troposphere and eventually drift up into the stratosphere. In 1974, Dr. Sherry Rowland, a leading laboratory chemist, predicted the possible effects these compounds might have on the ozone layer.
In 1973, Dr. Mario Molina joined my research group, and we were looking for a different kind of research problem for a laboratory chemist. And we decided we would try to understand what would happen to the chlorofluorocarbons in the Earth's atmosphere. And so we went through the various things which happen to most molecules in the atmosphere. They get rained out or they get torn apart by sunlight. And none of those things happen to the chlorofluorocarbons. We realized that the only fate that they would have would be to be destroyed in the upper atmosphere, in the stratosphere. And then we asked, well, when they are destroyed up in the stratosphere, then what? When they're destroyed, they release chlorine atoms, and the chlorine atoms proceed to attack ozone. And each chlorine atom can take out about 100,000 molecules of ozone before it actually is removed itself. At that time, the major use of chlorofluorocarbons was as propellant gases for aerosol sprays. And the idea that the use of underarm deodorants could somehow affect the Earth's atmosphere seemed bizarre to many people. And people asked legitimately for any kind of proof. And in 1975, the experiments went into the stratosphere, brought back samples of air, showed that the chlorofluorocarbons were actually there, and that they were disappearing with altitude as expected from the Rowland-Molina theory. And in 1976, we had the first action for calling for regulations that the U.S. government said that we would put restrictions on the use of the chlorofluorocarbons as propellant gases in aerosol sprays. For about 2 years, from our first publication until the National Academy of Sciences committee said that the science looks right, there was a lot of argument, a lot of opposition until about 1988, I think, that there's a time I would say that the industrial understanding began to agree completely with the atmospheric scientists' understanding. And from then on, there's been strong cooperation in the United States to get rid of the CFCs as fast as we can.
This issue was debated for years. There were a lot of different theories about whether or not ozone depletion was even happening.
There are several stations in Antarctica where ozone's been measured for a long time. The station with the longest record is the British Antarctic Survey's station at Halley Bay. They've been measuring ozone down there since 1957. There are also measurements that go pretty far back from the South Pole and from the Japanese station at Showa. For about the first 20 years of the British Antarctic Survey's measurements, the ozone stayed relatively constant. Sometime around the middle of the 1970s, the ozone began to drift downwards. It was found in the late 70s that in September and October, the spring months in the southern hemisphere, the ozone was thinning out more and more each year over a larger and larger area. The measurements have also shown that each year there's more and more chlorine in the atmosphere. Because chlorine in these amounts does not normally occur in the stratosphere, scientists believe that it's coming from the CFCs that have worked their way up from below. The evidence indicates that chlorine in CFCs is released into the stratosphere as sunlight breaks up the CFCs. Basically, it amounts to a conversion of chlorine from forms that don't destroy ozone into other forms that do. Each single chlorine atom reminds how rare our ozone really is.
By the late 1980s, more and more scientific evidence suggested that the chlorine from CFCs in the stratosphere would eventually deplete ozone globally. The evidence was strong enough that representatives from many of the world's CFC-producing nations met in 1987 to sign the Montreal Protocol. They agreed to cut production of CFCs in half by 1999. Following the discovery of what people called the ozone hole, and evidence that it was caused by chlorine, the Montreal Protocol was reinforced and CFC production was reduced even more. Some countries have said they plan to phase out CFC production entirely in the next few years. Ozone depletion in the northern hemisphere led President Bush to announce in 1992 that the United States would speed up its required phase-out of CFC production. As ozone is lost globally, more people may be exposed to increasing levels of solar radiation. But since nothing like this has ever happened before, scientists don't know exactly what to expect.
Medical scientists do know that exposure to ultraviolet radiation can cause certain disorders in humans. These include things like skin cancer, eye cataracts. UV exposure can also affect your immune system. Therefore, it's very important for us to understand how ozone depletion may either stimulate or increase these types of problems. One of the difficulties that we have in assessing the effects of ozone depletion is that the predictions are based on mathematical models. And these models are merely simulations and are not capable of giving us the exact types of increases that may occur. And to make it even more complicated, when scientists make predictions about possible medical problems that might result from exposure to the sun, they also have to consider the lifestyles that people choose. It's very popular today for people to live and visit sunny places. People love to sunbathe and swim and spend time outdoors. All of these activities expose them to more sunlight and perhaps to more medical problems from exposure to the sun. Separating the effects due to declining ozone from those due to changing lifestyles is not possible. So there's still a lot of scientific investigation that needs to be done before medical predictions can get really accurate.
Most scientists agree that the phase-out of CFC production will eventually stop ozone depletion. But we can't expect everything to change right away. CFCs have a long life, 75 to 100 years. It takes them 10 to 20 years to drift up into the stratosphere. So what we're measuring right now is a result of CFCs that were manufactured in the early 1970s. The ozone layer is now being watched very closely all over the world. New discoveries are constantly being made as scientists test their theories and uncover new information about how human activities may impact ozone depletion. We need to remain objective and open-minded about the evidence. We must try to gather together as many facts as possible because we still have to make many serious decisions about this issue. Here are some things that you can do to lessen the impact of ozone depletion. Be a responsible consumer. Try to buy products that don't use CFCs, but don't panic. CFCs are being phased out. Few products now contain them. Encourage your parents to maintain the refrigerators and car air conditioners so they don't leak CFCs into the air. If repair is needed, they should make sure that the CFCs are recycled. And when it comes to protecting yourself against the effects of ultraviolet radiation, use common sense. Protect yourself against overexposure to strong sunlight. Some aids that are helpful are sunscreen lotions, sunglasses, and hats. The best protection is to limit your exposure. I hope you'll be with us for the next program in the Chevron Video Showcase series, EcoSpeak, Coming to an Understanding. In the United States, spray cans no longer contain CFCs. Air conditioners and refrigerators in good condition do not release CFCs into the air. But when they break down, CFCs may leak out of them, so maintenance is very important. When these appliances do break down, the CFCs should be recycled.
There are many different techniques for measuring what's in the atmosphere, and I'll just describe two. One of them is called spectroscopy, in which you put through the sample, and the sample can be just through the air itself, and various wavelengths of radiation. For instance, red light, yellow light, green light, all coming from the sun. If you have a molecule which, for example, absorbs green light, then by measuring how much red light gets through and how much green light fails to get through, you can calculate how much of that molecule is in the atmosphere. Now, in a more complicated way, that's the basis of spectroscopy, of measuring individual wavelengths of light. A separate technique is to go someplace with a canister that has been emptied of air in the laboratory, open it up, and bring it back to the laboratory to investigate it. And that's the characteristic of these canisters. And it's an interesting fact that if you were to take, if you take a canister like this to the South Pole and open it up, that's enough air to tell what's in the atmosphere on a global basis. You can measure all of the chlorofluorocarbons. You can look for hydrocarbons as well. The sensitivity of our instruments is sufficient that one canister like this carries the signature of the gases that have been put into the atmosphere all over the world.
When the ozone hole was first discovered by satellite observations, we actually had very little knowledge about the polar regions in the upper atmosphere. We simply hadn't studied this region. And so people had various ideas of what might have caused this massive ozone depletion. So what we had to do was spend several years actually studying this problem very carefully. And we began flying airplane missions into this region in the winter. It's quite dangerous because it's dark, it's perpetually dark. There's no place to land if your plane has trouble. And so we have to be extremely cautious. And what we found was very high levels of chemicals that are related to the chlorofluorocarbons, or CFCs. These are the chemicals that are used in air conditioners, in refrigerators, and so on, that have long been linked to the possibility of ozone depletion in the stratosphere. We've all heard of the CFC theory of ozone depletion that first came out in the 1970s. Well, that theory had never actually been proven, although there was quite a bit of debate about it. And now here what we were finding was that through some very special circumstances, the chemicals, the CFCs, were actually causing this ozone hole to occur. The special circumstances were very unique to the polar region, and particularly in the southern hemisphere. And it had to do with the spinning motion. That actually had something to do with it, because that spinning motion isolated a large air mass over the South Pole in the winter. And that allowed this air mass to cool down to very low temperatures. Some of the lowest temperatures on the whole planet Earth occur in the winter, in the stratosphere, within this spinning air mass. And under those conditions, very unusual clouds were forming. These clouds had never been detected before and are found nowhere else, as far as we know, in the solar system, just on the Earth in this one region. And they were called the polar stratospheric clouds. And they're made of nitric acid, not of water like normal clouds. So they're very unusual. These clouds were causing the CFCs to deplete the ozone layer by activating the chemicals on the CFCs in an unusual way. And what we found when we flew into the ozone hole were that the chemical activity of the CFC-derived compounds were very, very high, 100 times higher than in the normal atmosphere. So that nature had, by isolating this air mass over the South Pole, by producing these unusual nitric acid clouds, was performing a very large-scale experiment in chemistry in the upper atmosphere that results in almost complete loss of ozone wherever these clouds form. And this provided further evidence that CFCs can indeed deplete the ozone layer.
There are certainly lots of things that can make ozone fluctuate, can make ozone in one year be greater than it is in another year. Probably the most important one is atmospheric meteorology. Just the changes in the weather patterns of the winds in the stratosphere have a big effect on ozone, and you can see 20 or even 30% changes from one year to another, especially at high latitudes. But that's a very different thing from a trend. That's something that just goes up and down but doesn't have any systematic trend over a time period of, say, 10 years or 15 years. Another process that can cause fluctuations from year to year are changes in the activity of the sun. Things like how bright the sun is certainly influence how fast ozone is produced by solar light acting on the atmosphere. But again, that's something that is typically cyclic. For example, there's an 11-year cycle of solar activity that causes a few % change in ozone, and we see ozone go up and down over that time period by a few % globally. But it's something that responds and comes back to where it started from after a period of, say, 10 or so years.
It's not possible yet, but it's something we'd like to put more thought into. The biggest job right now is to get rid of the chlorofluorocarbons that are causing the problem, and the world is working hard to do that. The industries and governments of the world are giving that a good try, and we hope they're going to succeed. But what we're worried about is that even after we get rid of the root causes of the ozone depletion problem, namely the chlorofluorocarbons, we know that the problem is going to persist for another 80 or 100 years. That's how long these CFCs survive in the atmosphere. So what we'd like to give some thought to for the future is, what if after we deal with the root cause of the problem, there's still more work to be done? Some way to try to clean out the mess, so to speak. We thought of an idea whereby if you could put the right kind of chemical into the stratospheric ozone layer, a kind of seeding effect, if you could put the right kind of chemical into the atmosphere to convert those chlorine atoms from one form, namely free chlorine atoms, into HCl and chlorine nitrate the same way nature does, but to just enhance the conversion, then that would render the chlorine atoms not dangerous with respect to ozone anymore. So we thought of a lot of chemicals and eventually came up with two chemicals, ethane and propane, very much like what is in bottled gas. And because of their chemical properties, we decided to do more. They look good. We decided to do some more calculations. Unfortunately, it's not as simple as that. There are so many other chemicals at play in the ozone layer, and we have not characterized well enough yet how the stratospheric ozone layer works in detail, that we cannot safely predict that adding these ethane and propane chemicals would stop the ozone depletion, even if we could add them correctly. But all ideas have to start somewhere. We have stirred up a little bit of interest amongst other scientists. And I have to say, it does not look very hopeful right now that this idea is ever going to work. But we at least wanted to put forward an idea that other people could think about and that we could continue to develop.
The health effects on people is a very serious problem because there are certain aspects of human health that are actually affected by exposure to ultraviolet radiation. But for people, the problem may not be quite so serious because we're aware of what is happening. We can put on sunscreen, we can wear hats, we can put on more clothes. People know to stay indoors on days when it's very bright and sunny, and we can reduce our exposure to sunlight. A larger problem occurs in terms of plants and animals that are living out in the environment. A tree can't pick itself up and go sit in the shade. It's going to be exposed to the full effect of solar radiation that's reaching the Earth's surface. And it's these organisms for which we're concerned in terms of ecosystems and the natural environment. We have found that organisms have various abilities to actually tolerate UV exposure, and many organisms, because they're in the sun all the time, are quite capable of protecting themselves. We have plants and animals which can contain chemicals that actually filter out UV and work in the same way as putting sunblock on your skin. We have organisms that are capable of actually repairing damage that's been caused to ultraviolet light. What we don't know, and the investigations that are taking place now are trying to focus in on this, This is what are these range of abilities, what's the upper and lower limit that organisms have in terms of UV exposure. And if ozone depletion continues to occur, will the increase in UV radiation that's taking place actually be able to be tolerated, or is it going to be too much for organisms to actually withstand? Now, one of the additional problems that comes with this tolerance is that different kinds of plants and animals have different levels of tolerance. So organisms which are very sensitive to ultraviolet light will actually either be reduced in numbers or may be removed completely from the system. And we're very concerned about what these types of changes might do in terms of interactions between plants and animals.
If you were to launch space shuttles on a regular basis, one a month, which we unfortunately have not been able to do from the point of view of space science, you would build up a chlorine level in the stratosphere due to the space shuttle. It would be about 1/3%, that due to the chlorofluorocarbons today. And so if you were to almost double the current rate of shuttle launches, then you would contribute to the overall background level of chlorine of about 1/3%. And that would be, again, responsible for some ozone depletion. You have to judge whether or not the space shuttle collectively is a benefit to mankind in terms of the observations it makes from space. And if one way of looking at it is that's the mechanism partly for launching satellites and observing the Earth and monitoring the environment. And so it's a shame that it has to degrade it somewhat, but again, the scales are relative.